This is the STS-119 interview with Mission Commander Lee Archambault. Lee, could you tell me what it was that made you want to become an astronaut?
Well, growing up in the Chicago area, Andre, I had a long interest in the space program ever since myself and the rest of our nation followed the lunar missions back in the 60s and early 70s. So the idea of becoming an astronaut's always been in the back of my mind, but it really wasn't front and center till I got well along in my military career. You know, I spent about 10 years as a operational pilot and then transitioned to be a test pilot. And it was at that time when I was serving as a military test pilot that I started asking myself, well, what's next in my military career? And NASA has a long history of using military test pilots to pilot its vehicles, so I thought this would be a nice logical extension of my career as a test pilot. So it was at that point that I put an application into NASA and was fortunately selected with Group 17 of the astronaut class.
Okay, you touched on the test pilot part of your career. Can you recount the educational and other professional path, the parts of the path that you took to get to NASA?
Sure. Coming out of high school in the Chicago area, I went to college at the University of Illinois, attained both a bachelor's and a master's degree in aeronautical engineering from the University of Illinois in Champaign-Urbana. Completing my master's degree, I went on to my Air Force career. And again, I spent 10 years as an operational pilot, transitioned to be to the test pilot corps, kind of made a mid-course adjustment in where my career was taking me in the Air Force, and decided to go towards the test field where I could then use my educational background directly and continue to fly aircraft. And switched from my test pilot career over to NASA when I was selected in 1998.
Tell me about the place that you consider your hometown and how that place influenced you and the things that you've accomplished.
I grew up in the Chicago area. You know, my mother actually was born and raised in the city of Chicago. My father just a few miles outside the city. Since I was 2 years old, and actually through my days in college, we lived in a very near western suburb of Chicago called Bellwood. Bellwood's about 4 miles due west of the city, and without traffic, it's only about a 15-minute drive to downtown Chicago. So, you know, we're right smack dab in the middle of the Chicago metropolitan area. And Bellwood's a village of about 20,000 people, and it's mostly a hard-working, blue-collar class neighborhood. And folks in Bellwood have a unique relationship with NASA that goes way back. It actually goes back into the 60s. Bellwood is a home of a former astronaut who walked on the moon, Eugene Cernan. And when Mr. Cernan was in the middle of his days at NASA, particularly flying the Gemini missions and the Apollo missions, he was the main business in the town of Bellwood, and we followed his career closely. And I can remember vividly standing in a parade when I was about 6 years old, honoring Mr. Cernan's first mission in the Gemini program. So we followed Mr. Cernan's career along quite well, quite closely, and it was interesting to see him walk on the moon, and actually still has to this day the distinction of being the last man to walk on the moon.
What or who was it that helped you realize the value of education in life and in attaining things?
Probably a conglomeration of several people. Certainly my family, my friends, teachers I grew up around. My parents, as I mentioned, both from the Chicago area, neither of them went to a university. It just wasn't in the cards back then. Their families didn't have the money to pay for it, and they didn't have that opportunity. My mother ended up becoming a nurse, my dad a fireman in the Chicago area, and they both worked a lot of extra part-time jobs and overtime in addition to their primary jobs to make sure both myself and my sister had the opportunities that they didn't. And when I was able to go away to college at the University of Illinois, I was determined not to waste their hard-earned their money.
Well, one of NASA's missions or goals is to inspire the next generation of space explorers. What do you think? How do you think NASA should be doing that?
Just what we're about to do, and that's going to get set forth on this Constellation program with the Orion vehicle. When I was growing up in the 60s, and again in the city of Chicago, and following our space program, we were watching Neil Armstrong do something and go someplace that no man had ever gone before. You know, first person to ever set foot on the moon. So as a result, we were just absolutely engrossed in our space program, and how could you not have been interested in the U.S. space program at that point? Today's young adults, our youth, whether they're in high school or even college, They don't have that perspective of exploring the unknown. Basically since the day they've been born, we here at NASA have been drilling holes in the sky about 200 miles up with our shuttle program and International Space Station program. And I say that not to diminish the great accomplishments of both the shuttle and the ISS program. They've both done a tremendous job opening up our different areas of space exploration that we hadn't seen before. But I merely point that out to show us the perspective that today's children have, which is different than my generation had. Today's children have not seen us explore the unknown. But when we start doing that again with the Orion and Constellation program, when we go to the moon for the first time in their lives and go on to Mars for the first time in history, these young adults will be just as inspired, if not more, than our generation was when we saw Neil Armstrong walk on the moon.
How has preparing for this space mission, your first as a commander, differed from your first ever space flight, from preparations for that?
Right. As a pilot on my first mission, STS-119, I zeroed in on exactly my specific duties on that flight, those being the pilot duties, learning the systems on the right side of the cockpit, and also serving as a robotics arm operator. I focused and was completely dialed into those duties and really paid attention to little else what was going on, so to speak. You know, I left that for my crew members to worry about. On this mission as a commander, I need to take a more global perspective of the whole mission. And I need to also allow the other crew members to become the experts on their individual fields. I stand back. I'm not really the expert on any one of the fields, although I have a little knowledge on all the fields. But I need to let them become the individual experts and trust them to take care of their job and leave them alone to do their job the way they know how to do it. And so it's trying to just more or less be a chess player to assign the individual crew members to the right job so that ultimately we can accomplish our mission objectives.
Tell me a little bit about what it's been like training with these crewmates for this mission, and if you'd like to kind of expand on particular skill sets of each crew member, feel free to do that too.
Well, these crewmates have been absolutely tremendous to work with, and I've told every single one of them from the very start, I wish I could claim credit for putting this crew together, but I can't. Steve Lindsay, the chief of our astronaut office, is the guy who makes the flight assignments. He gave me this crew, and I'm very, very appreciative. And in a lot of ways, I look at this crew and I say, boy, he really stacked the deck in my favor, and I'm very appreciative for each and one of these guys. They've been a joy to work with. Each one of them brings their own special talent to the table, and looking back at it, I'll say, boy, I'm really proud I selected this crew, but I can't claim that credit. It's all Steve gets all the credit on that.
Okay. Any particular crew members you'd like to give us some insight of their skills that make the team gel at all?
Yeah, I can touch on every single one of them.
Yeah, feel free. That's great.
Tony Antonelli, our pilot, consummate pilot, professional in every way, shape, or form, and he's a systems expert. He really brings a lot to the table in the entire flight regime, but in particular our ascent and entry training. Our mission specialist number 1, Joe Acaba, first-time flyer, has done a wonderful job. Joe is, I call him a jack of all trades. We've got Joe doing ascent entry flight deck work. In addition, he's a shuttle robotics arm operator. He's also doing a couple of EVAs out the door, and he'll be an IV for a couple other EVAs. So he's getting a taste of everything, and he's doing, for a first-time flyer, he's got a full plate, and he's doing everything quite well. Steve Swanson, our mission specialist number 2, our flight deck engineer, is also our lead EVA man for the team. I flew with Swanee on STS-117. There again, he was also the mission specialist too, and he was a perfect fit for the job. He knows the systems up and down very well. And on this mission, he'll be our lead EVA person, basically in charge of the execution of all 4 EVAs. He is a perfect man for the job. His skills are well respected throughout the entire office in the EVA world. Down in the middeck, we've got Ricky Arnold, another first-time flyer, and he came to us with some outstanding credentials in his EVA skills training prior to getting assigned to this mission. Ricky will be Steve's right-hand man, assisting him with all the EVA planning and execution. Ricky will also be performing 3 of the EVAs, one of them as the EV-1. And when we finish this mission, I fully expect Ricky will be the next Steve Swanson in our office. Moving over to MS4, John Phillips. John brings essentially all the experience to the table for our crew. John's a veteran of not only a shuttle mission, but also a long-duration mission. You know, I'm relying on John a lot to handle all the mid-deck operations as well as the space station robotic arm operations. In addition, he's my glue as far as allowing our crew to bond and work closely with the station crew. John knows both ends of the stick on this one. He's been a station crew member as well as a shuttle crew member. And finally, our shuttle rotating expedition crew member, Koichi Wakata, is just phenomenal. He's a great robotics arm operator. He's going to be a great long-duration space station crew member, and he's been well tasked by our crew, and he's doing everything quite well in training.
Okay. It's a perfect transition into the next question. With several Japanese Space Agency components now on the station complex, JAX has become a full-fledged member on orbit on space station. Koichi Wakata will stay there, as you mentioned, as the first long-duration space astronaut for JAXA. How does it feel for you to have a part in attaining that milestone?
We're very, very proud to have Koichi as part of our crew. Koichi's been an absolute joy to work with. He's a phenomenal astronaut, and just as important, he's a great person, and he's just been an absolute plus for our crew to have aboard. When we got assigned to take Koichi on this mission up to the space station, I had to decide how I really wanted to use Koichi. As you know, he's only a crew member, a formal crew member of our crew until Flight Day 3, after we dock, and then we get some of his gear transferred over to the ISS, at which point he then becomes a member of the Expedition 18 crew. And we absorb Sandy Magnus as part of our crew. So we only have Koichi formally as part of our crew for 3 days. So I had to decide how do we want to utilize Koichi. One avenue you can go down, you can look at it from, or perspective you can look at it from a commander's point of view, is that you might not want to task him to do too much because, for one, he's only going to be with your crew for a few days, and two, a lot of times his space station training doesn't overlap real well with our shuttle training. But from day one, Koichi came to me and said, hey, use me where you need to use me. I'm here for you to support the crew, and we've done that. I've decided to leverage his great skills, particularly in the robotic operations area. Koichi's going to be a very significant player in our early inspection on Flight Day 2. In addition, he's going to be doing a lot of robotic operations with John Phillips during our dock time frame. So he's a full-up crew member while he's with us. In addition, while he's becomes a member of Expedition 18, he'll still be working a lot of robotics operations with John. So he's been just a great addition to our crew, and I can't imagine how we could have done it without him. You know, we're very proud to have Koichi aboard.
Okay. There are thousands of people that work behind the scenes to make this and all space missions happen. Tell me how you feel about their contributions and what it's like when you do get to meet these people.
Yeah, I mentioned before when we talked about my hometown, I grew up in a hard-working blue-collar type town. I'm most comfortable when I get a chance to really meet the guys down on the level of turning wrenches and the behind-the-scenes guys. I feel like I'm one of them, and I enjoy being part of them. And I always look forward to the opportunity to spend a little time with these folks, whether it's here at JSC or at the Kennedy Space Center. I never pass up the opportunity to thank each and every one of them for the great contributions they're doing, not only for our mission, but for our space program. It's an honor to meet these folks. They shoulder a big load. The safety and success of every mission is on their shoulders, and I'm very appreciative for all the good work that they do for our program.
Okay. Please summarize, if you would, the main goals of this mission that you'll be trying to accomplish.
We have two major goals. One is to safely get Koichi aboard the ISS and make him part of the Expedition 18 team. And the other is to bring our payload, the S6 truss, up to the space station, deliver it, and install it to provide the last and final segment of power generating capability for the space station.
Tell me some of what your main role and responsibility is for this mission as mission commander.
Sure. I believe I look at my role as merely to orchestrate all the other crew members to their assigned tasks so that we do accomplish our mission objectives. As far as my responsibility goes, I look at it as, number one, my first responsibility is overall safety for the crew, and two, mission success, and in that order.
Give us your best description, if you could, of the S6 truss and its attached solar arrays, and tell us how the station will change both in capability and look after it's installed and the systems are activated.
The S6 truss, it's about a 31,000-pound piece of gear. On top, attached to it on the very end are two solar array blanket boxes housing our solar arrays. We'll bring those up to the station and attach it on the starboard side to the S5 truss, which is currently up there. S5 is currently the most starboard existing truss segment that's out there right now, so we'll attach our S6 to the S5. As the station exists right now, we have 4 sets of solar arrays on the port side, but only 2 on the starboard side. So when we get up there, we're going to balance out the look, if you will. And for Swanee and I, this is kind of a role that's regenerating itself. We had the same role on STS-119, where at that point we balanced it out by bringing the starboard S3, S4 truss with 2 sets of with 2 solar array wings, and balanced out the look as it was then. Well, since then the program's managed to unbalance everything, and now we're going to get a chance to balance it out again. But in reality, in all seriousness, this is the final truss segment that's going to go up, and it houses the last 2 power channels for the space station's power structure. When we successfully install the truss, the station will have its full complement of 8 power channels.
Okay. How would you characterize the work that the STS-126 crew did on the starboard solar alpha rotary joint, and how that's impacted the relevance of your mission?
Sure. As we know, the STS-126 team spent several EVAs doing some repair work on the SARG, the rotary joint on the starboard truss. In first analysis, it looks like they did a pretty darn good job. The drive currents are way down, and I think it looks like we're on our way to getting continued and prolonged auto track capability again on the starboard SARG. For whether or not this turns out to be a long-term fix, only time will tell, but in the short term, it looks like they've been very, very successful with their EVAs in repairing and lubricating that starboard SARG. And this has a direct impact on us in that we're going to be attaching our S6 truss to the starboard side, so the better that SARG can auto track, the better the existing truss segment out there will be in generating power as well as ours.
On flight day 1, you'll launch aboard Discovery and check out and configure systems for your stay in space. Then on flight day 2, a limited inspection of the station's exterior. Can you just walk us through a bit of an overview about how that inspection is going to happen?
Right. Well, we are transitioning from flight day 1. And flight day 1, it was a very condensed, lots of activity. 6.5 hours from launch till the time we go to sleep, and it's a beehive of activity. Flight day 2 is almost a reversal of flight day 1. Things tend to slow down a bit. What occupies most of our day, as you just mentioned, was our early inspection, the flight day 2 inspection. This is about 5.5 to 6 hours of inspection work using our space shuttle robotic arm. Tony Antonelli, Joe Acaba, Koichi Wakata, John Phillips, and myself will be the primary operators to participate in that inspection. The inspection is actually 3 different individual inspections consolidated into one. It starts out with the starboard leading edge wing inspection, then it goes from there to the nose cap inspection, and finally ends up with the port side inspection. It's very tedious work, and you're operating the inspection boom within very close proximity of the orbit for an extended period of time. So for that reason, we've decided to go ahead and switch up the lineup for each of the individual components of that inspection. The idea here is not to let anyone get too complacent and to keep everyone focused on the job at hand. In addition, Flight Day 2 presents a couple of some more additional, not necessarily problems, but that's the day that most folks find that they're adapting to living in space. You're almost too busy to think about it on Flight Day 1, but on Flight Day 2, your body is now finally trying to adjust to prolonged life in zero-G, and that's when your senses are trying to get used to a zero-gravity environment. So we have additional challenges that we don't normally have for the remainder of the mission. So for that reason, we switch things up quite a bit on Flight Day 2 as far as the lineup goes between each of the individual inspections. And while that's all going on, we have Ricky Arnold and Steve Swanson down in the airlock doing a lot of inspection and transfer preparation for their spacesuits that they'll be using on the EVAs.
Okay. The next day is the first of several very busy days to come for the crew. Onboard shuttle and onboard ISS. You'll be going through the rendezvous and docking maneuvers. Can you talk about how that will happen and what you'll be doing for that procedure?
We get in our rendezvous timeline real quickly after we wake up. About 90 minutes after the crew wakes up, the core rendezvous team, which consists of myself, Tony Antonelli, and John Phillips, will jump into the rendezvous timeline. The rendezvous timeline starts about 5.5 hours approximately before the actual docking. For the first 3 hours, Tony and myself, assisted by John, will conduct a series of burns, some ohms, some RCS burns, to position ourselves in close proximity with the orbiter. And at the end of those 3 hours, we'll conclude that with what's called a TI burn. With the successful completion of that TI burn, for all intents and purposes, the orbiter will be on sort of a collision course with the space station. Once we finish the TI burn, our roles, we play musical chairs with where we're at in the cockpit. I will transition from the commander seat to the aft flight deck, where I'll be at the controls in the aft flight deck and also looking out through the overhead window. Tony will jump over from his seat to mine, and that's where we bring Joe Acaba into the pilot seat, and Joe will assist Tony executing the checklist procedures. For about the next hour and 15 minutes after that, Tony, assisted by Joe, will perform a series of very small correction burns to place ourselves at the end of that fourth correction burn, to place our orbiter within approximately 2,000 feet coming up the station from slightly behind and slightly below. At that point, I'll begin manually flying the orbiter. I'll initially fly it to a point directly below the station at about 600 feet, and that's where we kick off the RPM, or the rendezvous pitch maneuver. Tony will actually program the autopilot to do this maneuver, and it'll be a pure 360 directly underneath the station at 600 feet. And that's where the station crew members can take some very good shots of our TPS, or our thermal protection tiles on the belly of the vehicle. Coming out of that pitch maneuver, I'll again take manual control of the vehicle, and I'll fly what's called a torva, where I transition the vehicle from that point 600 foot below the station to a point about 300 foot out in front of the station. And from there, essentially, I'll just back it right on in and rendezvous with the space station. Ultimately, when we dock with the station, we're moving at a snail's pace of about 1 to 2 inches per second. And so you can see it was a full, well, we had 4 guys working actively on this part of the process, and once we do dock or make contact with the station, that's when Swanee and Ricky will take over operating the APDS, or the docking system, to perform all the hook closures and make sure we have a good tight seal with the space station. And while all that's going on, we've got Koichi running all the photo and TV gear to capturing all the video that you're going to see here down on the ground. So it's a complete team effort. There's no one that's just sitting around on this one.
Then on flight day 4, the focus turns to S6 and some joint robotic works between the shuttle and ISS. What's the plan to get S6 out of Discovery's payload bay and to the point where it will remain overnight?
Yeah, Flight Day 4 is a major robotics day, complete robotic operation from start to finish. We'll start the day out with John working with Sandy Magnus on in the Space Station Robotic workstations, the Space Station Robotic Arm Robotic Workstation. They'll use that arm to unberth the payload from the payload bay of the orbiter, and they'll maneuver it sometimes within mere inches of contact with the orbiter structure. So it's a very, very meticulous process, and the degree and the accuracy to which they're flying to is really amazing. They'll get the payload successfully out of the bay, and they'll maneuver to a position where they can then hand it off to the Space Shuttle Robotic Arm. The Space Shuttle Robotic Arm will be flown by Tony Antonelli and Joe Acaba, and they'll also grapple the payload. So now we've got the payload dual grappled. But once Tony and Joe report that they have a good grapple on the payload, then Sandy and John will then ungrapple the payload with the Space Station Robotic Arm and maneuver it manipulate the arm into a maneuver position. At this point, once they get that Space Station Robotic Arm manipulated to this what we call a maneuver position, the ground team will then take the the MBS, or the mobile base system, which is where the space station robotic arm is located, and they'll move it on essentially on a railroad track, completely starboard to what we call worksite 1, which is the furthest starboard position you can put that MBS, and it's out near the S3, S4, just short of the solar array or rotary joint. It's at that point the station robotic arm can then re-grapple the truss and then maneuver to what's called an overnight park position, an ideal position for thermal reasons, where we're going to keep that truss segment overnight. So it's quite an orchestration of robotic events that our ground team, headed up by Andrew Clem and Steve Rowley, have done a super job orchestrating this chain of events.
Any good plan includes a contingency plan. Can you give us some idea of what options are in place, what backup plans are in place if, for instance, you're not able to get S6 out of Discovery's payload bay in the unlikely event that one of the arms fails?
Okay. First let me say that we cannot do this mission without the space station robotic arm. It's impossible to get the task done without the big arm, as we call it, on the space station. In addition, another complicating factor is the fact that we cannot even unberth the payload with the shuttle arm. Due to geometry now, with the Japanese lab out there, the shuttle arm would run into interference with the Japanese lab. So our only way of even unberthing the payload is now also with the space station robotic arm. Fortunately, the station robotic arm is very redundant in many ways, and it's checked out quite extensively before we launch to get on orbit. So we'll have a lot of confidence that that arm will work well. But if the station robotic arm were to fail catastrophically when we showed up out there, it's impossible to perform this task. Now, the shuttle robotic arm, on the other hand, depending on where and when the failure and the nature of the failure might occur, the ground team might have some options for us. There's a possibility we can put the payload on the POA, or the payload ORU attachment system, which is essentially an end effector that's mounted on the MBS, the mobile base system. Or there's even a more remote chance that perhaps we can translate that payload with the S6 attached to the station robotic arm, though this would take a lot of extra analysis. So again, if we ran into those problem with the shuttle robotic arm, the ground team would have to weigh in quite heavily and do a lot of analysis. There might be some workarounds there, but there is no workaround if the station robotic arm were to fail.
Okay. The ambitious schedule continues on the next day with the first spacewalk of the mission, which is all about getting S6 into position and then attaching it to the station. Can you walk us through, give us an overview of how that's going to happen?
Sure. Flight Day 5 is the home for EVA-1. And I'll talk to you a little bit about the EVAs in general. For starters, Tony Antonelli is what we call our suit-up IV. He'll be the guy assisting the EVA crew members in the airlock getting ready before the EVA as well as after the EVA. Now on EVA-1, the lineup here is Steve Swanson will be EV-1. He'll go out the door with Ricky Arnold, and Ricky again will be in the EV-2 position for our first EVA. On the aft flight deck of the orbiter, Joe Acaba will serve as the task IV, and he'll actually be choreographing the entire EVA with a checklist that he'll be running from the aft part of the flight deck. In addition, we've got John Phillips and Koichi Wakata also performing robotic arm operations, and they'll be installing the truss segment with that robotic arm. So for starters, when Tony is actually suiting up both Swanee and Ricky, John and Koichi will be flying the robotic arm, taking that payload from its overnight park position and maneuvering it to what we call a pre-install position. This position is directly in line with the S5 truss and about 5 feet out. Once Swanee and Ricky go out the door on their EVA and they translate out to the S5 truss, they will then verbally guide John as he brings the S6 truss in its last 5 feet, and they will give it what we call a GCA and vector John in for a very precise alignment and contact of the S6 with the S5. Once we have a good contact there, Ricky will then drive a set of claws that are on the S5 around the capture bar of the S6 to stabilize the truss segment, and then Swanee will go around on the S6 truss at the 4 corners and actually secure 4 different bolts. And at the completion of securing those 4 bolts, the S6 truss will now become a permanent fixture on the ISS truss segment.
Okay. So S6 gets installed and the necessary power and data connections are made. Eventually, there's some other tasks on EVA-1. Can you give us the rest of the story for EVA-1?
Yeah, the rest of the story for EVA-1 is all about the S6 truss. After we get that truss segment installed and bolted onto the ISS truss segment, Swanee and Ricky will perform a series of tasks to prepare that truss for solar array deployment, which is currently scheduled for Flight Day 8. So Swanee and Ricky will be releasing several attachments so that they can then take the blanket boxes and maneuver them out from their stowed or their transportation configuration, how they have the blanket boxes tucked away for flight on the orbiter or as we go uphill. They'll then just deploy the blanket boxes. They won't deploy the solar arrays, but they'll get the blanket boxes spread out. In addition, they'll do some work to deploy the radiator, and they'll remove a few covers that are on the electronics components of the S6 truss.
Okay. You mentioned earlier that you and Steve Swanson had a similar mission with the STS-117 and installing the S3, S4. Was any lessons learned for you two that will be helpful in this mission with that?
Well, unfortunately, there's not as far as attaching the S6 truss to the S5, there's not a lot of lessons learned from our mission, because on an STS-117, mission 13A, when we attached the S3 truss, that was actually, we were able to fly that attachment, or actually install a truss without the aid of the EVA crew members. Matter of fact, we did that before the EVA crew members even got out there. And we used what we're using with the robotic arm is what's called a space vision system, or an SVS system, to give us precise alignment. In addition, the bolts that we drove that secured the S3 truss to the ISS were driven from inside the vehicle, or IV. Neither of that is the case for what we're about to do. However, what we are about to do with the S6 truss is identical to what the STS-120 guys did when they installed the P6 truss on a P5. So a lot of their lessons learned have been carried over and been incorporated in our training by our instructors.
If mission managers decide that they'd like to take a closer look at Discovery's exterior once you are docked, it's called a focus inspection. Tell us how that will happen.
The focus inspection is currently planned for Flight Day 6, the day after our first EVA. The focus inspection will be performed with the same inspection boom that we use on Flight Day 2 if we do have to do the focused. Unfortunately, or for the same reason that we can't take the payload out of our bay with our shuttle arm, those same interference reasons drive us having to use the space station robotic arm to take the boom out of the bay. So John and Koichi will start out by unberthing the OBSS, the inspection boom, from the shuttle's payload bay. They'll hand it off to the shuttle arm, which again will be flown by Tony Antonelli and Joe Acaba. At that point, both Tony, Joe, and myself will serve as the primary inspection team, and we'll fly the focus inspection to wherever or whatever that the ground team wishes to inspect that day. Of course, we won't know any of the details until we have to do it, hopefully not. At the completion of the inspection, once again, Joe and Tony will have to hand off that inspection boom to the station arm, and then John and Koichi will rebirth the boom back into the payload bay of the orbiter.
And there's a chance that you might not do a focus inspection on the day that it's been timelined for. If that becomes the case, what will happen on that day?
Right. Hopefully not. Hopefully we won't have to perform the focus inspection. And if that's the case, then what we're going to do is move up the solar array wing deployment, which is currently scheduled for Flight Day 8. We're going to move that up to Flight Day 6. Now this opens up a big gap on Flight Day 8, and what we'll do there is that'll just allow us more time for some transfer operations.
Okay. Can you walk us through how that solar array deploy will happen?
John Phillips is going to be in charge of running the entire operation, at least from our activities inside the vehicle. John's going to employ basically the entire shuttle team, as well as a couple of space station crew members, to be focused on and looking at various points on the solar array wing as we deploy it. The ground team's actually going to start the process, and they'll do about the first 15 or 16 steps of the procedure, including unlatching the blanket boxes and deploying each one of those solar array wings approximately one bay. And what When the solar array wing is fully deployed, it's deployed out to what we call 31.5 bays. So the ground team will deploy it just the first couple of percent of deployment. Now the actual deployment of the solar array wings has to be done in daytime. One to enhance our viewing of various points on the solar array wing, and two is when we deploy it, we'll deploy it in segments. We'll deploy it out to about the halfway point, roughly 50% deployment. Then we have to sit and let it bake in the sun for about 30 minutes. This bake time is to reduce the effects of what we call stiction, and that is where the panels of the solar array want to stick together because they've been stuck together for so long, and allowing it to bake in the sun tends to reduce those effects. And after that 30-minute bake out, then we'll deploy from about the halfway point to a full deployment. Each one of those deployments from the start to about the 50% point, and then from 50% out to the full, takes about 5 minutes each.
This business of dealing with solar arrays has been unpredictable in past missions. Are there any updated procedures in place because of past issues with solar array deploys?
Well, first of all, I mentioned this 30-minute bake-out period. But we actually even incorporated that on STS-119 when we were deploying the solar arrays on the S3, S4 truss. In addition, there are some other areas that we need to key in on that have given us some problems when we deployed solar arrays in the past. For instance, where how the guide wires are feeding through the different grommets. We did have some problems deploying a solar array on STS-120. That's when we deployed the P6 solar arrays. However, keep in mind, that was a solar array that we were deploying in space for the second time. We had deployed it at one point, then retracted it, and then had to redeploy it. And we knew when we retracted it that we had some problems with that array, and so we kind of sensed that there might be some problems in the deployment of it, and sure enough, we did have some problems. But as a result, we now know some other areas that we need to focus in on. Hopefully that won't be the case with us as we're deploying our solar arrays for the first time. But there is one complicating factor, if you want to call it that. One of our arrays has actually been packed up in its box for almost 8 years, so we'll definitely have to have that good bake-out period that I mentioned at the halfway point during its deployment.
On the second spacewalk of the mission, Steve Swanson and Joe Archambault will tour the truss, so to speak. Can you give us an overview of the work sites they'll be at and what they'll be doing there?
Sure. As you mentioned, Swanee and Joe will be the EVA crew members on this EVA. Swanee will be going outdoor for his second EVA of the mission. Joe will be his first EVA of his career. Inside the flight deck of the vehicle will be Ricky Arnold, and he'll be orchestrating as a task IV that day. And as in all EVAs, Tony Antonelli will be assisting with the suit up in the doffing of suits after the EVA is over with. You're right, they will have a great tour of the truss in this EVA. They're going to start out on the far port side of the truss, the P6 area, to do some work on some battery prep work for a future mission. They'll then move inboard to the P3 truss and deploy a payload attachment system. This particular system is called a UCAS. They'll keep moving inboard to around the P1 area and do some plumbing work on some fluid jumpers and cable clamps. And finally, they'll transition to the starboard side for another payload attachment system, or pass deploy, on the S3 truss. So they did span the gamut of the entire truss segment, just about all the way from P6 and finishing up on the S3, which is about halfway out the S3 truss.
Assuming S6 has been installed and its solar arrays have been deployed and everything is fine to that point, you'll be doing some different tasks on EVA-3. Can you give us an overview about what's going to happen?
Sure. I'll start by talking about the lineup for EVA-3. And for EVA-3, Ricky Arnold will go out the door as EV-1, the lead EVA crewman, and he'll be assisted by EV-2, Joe Archambault. Steve Swanson will be the task IV from the orbiter flight deck. When the EVA starts, Joe Archambault will actually be riding with his feet connected to the space station robotic arm via an APFR. John Phillips and Koichi Wakata will be flying that robotic arm from the lab robotic workstation. They're going to their initial task is to relocate a CETA cart, or an equipment rack, that's on the railroad tracks, if you want to call it that, of the space station truss segment. They're going to relocate the CETA cart to better position it for a future shuttle mission coming up to the station in the near future. Once they complete that relocation of the CETA cart, Joe and Ricky will switch positions. Joe's going to get out of come off of the space station robotic arm, and Ricky will get on. And at that point, John's going to go ahead and fly Ricky over to the vicinity of the SPDM, the Special Purpose Dexterous Manipulator, which came up on STS-123. And Ricky's task will be simply to remove some MLI covers that are still on the SPDM. While this is going on, Joe's going to work his way on his own over to the S3 truss and perform some plumbing work on some jumper cables. At the completion of Ricky's work removing those MLI covers, he's going to get off of the station robotic arm, and he's then going to do some repair work and some lubrication work on the end effector. Very similar, actually identical to what Shane Kimbrough just did recently on STS-126 on the other side of the end of the space station robotic arm. So it's a myriad of tasks going on, and it's not directly related to our S6 truss, but once again, they're all tasks that the space station program has lined up to better prepare ourselves and put ourselves in a good posture for future and upcoming missions.
And what's the plan for the fourth and final spacewalk of the mission?
Yeah, the plan for EVA-4 has been a very dynamic plan. It's evolved over our training period, and until very recently, we thought we were actually going to be relocating a grapple fixture off of the P6 truss and moving on to the FGB. But late-breaking changes have occurred, as they always do, and when we have this very dynamic situation going on with our station, and we've now settled on to what we think is going to be the final scenario. And in this case, the lineup for EVA-4 will again be Steve Swanson with Ricky Arnold, and Joe Archambault will be indoors as the task IV. They'll start the mission with Steve, or Swanee, installing an antenna on the Japanese lab. And at the time Swanee's doing that, Ricky's going to be doing some IR imaging with a special camera he'll have outside. They'll come off of that task, and they'll then work together to install a wireless antenna that will be used in the future for wireless video during EVAs. And finally, then time permitting, they'll install up to 2 PAS. They'll perform up to 2 PAS deployments, PAS being payload attached system, on the S3 truss. And then that ought to wrap up the EVA.
Okay. After your work on ISS is done and your crewmates, or you and your crewmates are finished, you'll eventually depart the station. As you're pulling away, you'll get your first big picture look at a station completely transformed, with its solar arrays and its truss completely built out. How do you think you'll feel knowing that your contribution will allow ISS to do more with more people in the future, and reach its capability?
Right. If it's anything like what I felt in the last mission, is when we pull out for the undock and fly around, which our pilot Tony Antonelli will be doing. It's at that point, really for the first time, we'll probably actually look at the station and say, there it is. I mean, it'll be a real sense of mission accomplishment. We've done our job. We've delivered the S6 truss. We've installed it, and it's out there working and producing power for the space station. It's the first time that we'll really absorb it all. And by the way, that's also the first time we'll actually be able to send pictures to the ground, both stills and video to the ground, showing the space station in its newest configuration. When we do all that, the sense of accomplishment will be phenomenal. It'll be just like any other crew that's going up to the space station, whether you're on a mission to it's a construction mission where you bring up additional hardware, or you're going up there to bring very important logistics supplies, as the STS-126 team just did. We all feel equally a real sense of accomplishment that we're a small piece in this big puzzle of putting together this absolutely wonderful orbiting laboratory. And we certainly hope that both our nation and the nations of all our international partners can use and benefit from this wonderful facility for many years to come.